Good morning, everyone. I hope everyone is doing great, staying safe during this difficult times of COVID-19. Well, today I'm going to give you the lab instructions, and we'll be solving a lab tutorial, and I'm going to choose actually the same circuit that I chose during our regular lab session last week. So it's going to be kind of in a more detailed step-by-step methods so that you can use these instructions to solve your lab report, which will be released very shortly after the video has been uploaded. So this is the general interface of the LTspice, and we start by creating a new schematic. The circuit I've chosen is taken from your lecture slide, which is finding the resistor power. So we have the resistor power here. The statement says that there's a 560 ohm resistor connected to a circuit, causes a current of 42.4 milliamps flowing through it. We have to calculate the voltage across the resistor and the power it is dissipating. So the voltage is already calculated as 23.7 volts and power as I squared R as 1.077 watt. So the circuit requirements is a 560 ohm resistor and a current source supplying 42.4 milliamps of current. So let's start building that. I'll hit R, Control plus R to rotate the resistor here, and then escape. F2 for component search. We'll look for current source. Here's the current source. And okay, I've rotated the current source so that the current flows from ground towards the resistor. I'll put it somewhere here. And then actually that's it. And then I'll bring the ground. Here's the ground. Press in the G key. I'll put it somewhere here. Okay, F3 to wire the circuit. I'll start wiring. So I'm gonna wire it. Okay, and then the ground. So that's my circuit. For the current, the requirement was 42.4 milliamps. I'll right click the current source. I'll input the value of 42.4 milliamps, and that's it, 42.4 milliamps. And resistor is 560 ohm. Right click the resistor, put 560 ohm. Perfect. Now labeling your nets, labeling your nodes is a very important step. Please do not forget. Always label your nodes. This is very important when you start the simulation, and to identify the plots and the nodes. All right, so this is the symbol for label. We call it label net, which is used to label your different nodes. So I'll click that one. I'll just call this as VR1. All right, the first net, and I'm gonna put it over here. So my whole this whole whole net is labeled as VR1. So when I run a simulation, and I could find the parameter VR1, and I would immediately know that this VR1 is actually the voltage of a resistor 1, which actually we are required to find, which we have been asked here in this example to find that voltage, which is 23.7 volt. So the circuit is now completed. We have made a current source, a resistor, and a ground. Ground is very important. Your circuit will not run if you don't give it a reference, which is the ground in this case. So make sure you always give the reference to complete the circuit. Once it is done with the famous running man simulation command, so I'll click that running man, and then first of all, there are two ways to solve this circuit. So I can go and I can do the DC operating point analysis. And DC operating point analysis is mainly used to kind of find the voltages and currents or at every different element. So I'll have the current source and resistors. Say we have 4 more resistors, 4 more voltage points, 3 more different components with some current ratings. So if I do the DC operating point simulation, actually it's going to analyze my circuit and will give me the voltage and current ratings of every element's voltage and the current passing through each and every element. That's what we're going to get from the DC operating point, and it is going to pop up in the form of a list. But it doesn't give us the power. In LTspice, we have no way to kind of also output the power, and if there is one, then I'm not sure how to do that. So what we can do right now, we cannot use it for this very example because we are also asked about the power dissipated by the resistor. So the DC operating point will not give us the power. So in a way we cannot use it, but I'll still use it because this will be the requirement in your lab report. So if I'll do the DC operating point simulation, then I'll get .op, I'll do OK, I'll just put it somewhere here, and the window pops up which tells me that the voltage V, which is VR1, you see here, here. So it tells me that the V, which is VR1 here, is 23.744 volt. That's the voltage. And then the current I1 is 42.4 milliamps, which is actually set by S, and the current through the resistor R1. So that's all the parameters. So they are giving us the operating point. It's kind of I would say for this kind of very simple circuit, it's too much to do any kind of simulation, but we have to it's our task that we have to do that. So somehow we are doing that. So once that is done, I would like to delete that because we are still short of the power. So what I can do, I can kind of use a trick to simulate our circuit, the running man. I'll go to the transient. So transient simulation means actually it's a transient response of a system. What happens during first few milli or microseconds is of fundamental importance in all the circuits, in all DC as well as AC circuits. So what we will do, we are saying that the transient simulation will be running, there will be no transients in this system, so actually it won't matter a lot. So the parameters I'm going to set are these. So I'm saying that transient simulation stop time, so it's run this simulation for 2 seconds. It means the stop time will be 2 seconds. So the system will run its simulation for 2 seconds and then it will stop showing you the data. It will stop running the further simulations or further solutions. And then time to start saving data. I mean, when would you? I mean, which time interval is of your interest for saving data? So I would say just start saving data right from the first moment you start solving the example. Maximum time step, we don't have to give maximum time step again because this is not a time bounded simulation. We are not concerned with that, so I'll just leave that empty. I'll say OK, and then the immediately we see that the simulation command, the simulation window is here. So now if I bring my cursor here, I'll see that probe. So if I would like to find the voltage at resistance 1, I'll bring my probe here, I'll click over here, and you see 23.745 volts, somewhere here. I got that 23.745 volts. And to know the power of the system, so how would I get the power of the system? So I'll bring my cursor over resistor, and while I'm here on top of resistor, I'll press the Alt key. And pressing the Alt key, it changes it into kind of thermometer, and this gives us the instantaneous power that is being dissipated by the resistor. So I'll just click that, and you will see that the blue line here now shows me the power, and the scale for the power is here. It's around 1.0067 somehow. That's what we are expected to find. 1.007 volt and 23.7 volts. And if you just double click that thing 1 2, you will have the power on the left scale towards left y-axis, and the voltage will be gone. And you see, I mean, we have the voltage VVR1 multiplied by IR1 written here. So we exactly know that this power is being dissipated by this resistor when it is consuming the current I1, and the voltage drop across the resistor is VR1. That's our power. One way of finding the exact power number here, I mean, is by introducing the cursors. So we can always bring in the cursors. So for example, I'll click the VVR1, and you see that the first cursor appears here, and this window here. It tells me if I bring my mouse over the cursor, I can move it, and it will just stick to the line. It will stick to my simulation line. And it tells me over the horizontal area, you see over the horizontal window, it tells me the milliseconds, the time of the simulation, and the vertical value, which is 23.74399 volt, and it remains same because we can see it's a constant line, and the problem we are solving is for one single value, so it makes sense. To get the second cursor, I'll just click this one, and we get the second cursor, which will be here. And now my second cursor, again, this one, the horizontal tells me the time, and the power being dissipated, which is 1.00674555 volt, which remains constant. This is the way to attach cursor, just in case if you're interested in a specific time, if our simulation is time bounded, and the specific value during that time. That's how we can solve the circuits. We analyze the circuits. And one more interesting thing, just before I'll finish this tutorial, is how to simulate. Let me just close this simulation, or I'll keep it there. Let me open one more simulation. So what I'm going to do, I'm going to show you how to make a voltage dependent voltage source. So that's very important, and then you will be having one circuit solving that circuit. So I have to tell you that how to implement voltage dependent voltage source. So for let me bring one voltage source. So I have two, and this is the voltage source. So let's suppose I have one voltage source, which is called V1, and then I'll bring the search window, and I'll press E. E is going to give me the voltage dependent voltage source. All right, I'll bring it here. I'm gonna put it here, and then let me bring one resistor. Okay, so these wires, these are the output wires. So this plus these two nodes are the output nodes, and these are the kind of input nodes of the voltage source, of the voltage dependent voltage source. What do I mean by this? It means that these two wires will be sensing a voltage which will then be taken by a multiple, whatever is the multiple, and that output will then be driven at these 2 points. With this example, actually things will be easy. So what I'm gonna do, I'll take F3 line, start wiring the circuit, bring it here, done. Okay, done. Let me bring the ground. Ground is very important. F3, okay. And then F3, I'll bring this here, this one here. Okay, so that's my R. So let's suppose I have 5 volts as of a main voltage source, which is an independent voltage source, And this voltage source is a dependent voltage source. So the output voltage of this source, which appears over these two terminals, depends upon the voltage which is uh, given at this point at any time. So right now, what I'm saying that take this 5 volts. Imagine, I mean, so let's say, let me write. So let's suppose that I have 5V. My voltage dependent voltage source is taking a multiple of 5, and whatever is the voltage on my independent voltage source, it just multiplies that number with 5 and gives me that output. So I'll take, having said that, let me put this R value as 100 it's mega ohm. I just want to keep a high value so that the whole voltage appears just across this R1 resistor. So what I'll do, I'll just right click this thing, and this value is the multiple. This gives us the dependent multiplier. So I'll say give me 3. I mean, if it's okay, as I said 5, so I'll give it a 5. So what does it mean? Now, if I run the simulation, no, before that, the net labels. Net labels are very important here. So I'm calling the first voltage source as Vs. This is the voltage source 1, and that's my net label. And I'm going to call this one as V out. Actually, at this point, we can run the DC operating point simulation because we are just interested in the voltage. So I'll go to DC operating point. Okay, the window pops up, and here it is. So now you see that here. So you see that the voltage source Vs is 5, while the voltage out, which is the output of the voltage dependent voltage source, is 25, and this multiple 5 actually defines that voltage. So that's how you can implement the voltage dependent voltage source. We can change the multiple. Let's say it is 3. No, I'm sorry. I'll double click. I'll put 3. Okay. Run the simulation again, and you have 5 as the voltage Vs1 and V out as 15 volts. That's how you will simulate the voltage dependent voltage source. But again, remember, do not forget the source, the labels. Use intelligent labels for labeling your nets. Don't forget. Don't use the default voltage labels given by the LTspice. So you have to make sure that you're doing it properly. I hope with this tutorial you'll be able to work out on the lab report. Let me quickly see. Okay, this one is done. This is the lab report. Is there any specific information? Yeah, nothing. I mean, there's nothing important. I mean, I think I have covered everything that you will need to solve your circuits. If there's any question, you can drop me the line. Just write me an email, and I'll be able to answer your questions. I hope this tutorial was useful. The lab will be released after a few hours, and then you will have 1 week to submit the lab report. Everyone, bye bye.